Gravity is the man. Gravity is ever present and always keeping us down. Yet our understanding of it is vague at best. Even Isaac Newton, who gave us our first mathematical framework to predict the effects of gravity, admitted to having no idea as to how it worked. Then, it was Albert Einstein who showed us that gravity was an outcome of an interaction between matter and space that causes space-time paths around objects to curve. However, Albert never bothered to explain exactly how matter and space do this, or how this leads to gravitation and time dilation, which means general relativity is still incomplete and maybe even a little bit wrong. And even though Albert already attempted to correct the errors in general relativity with the cosmological constant, it still seems general relativity is stuck in a static universe, and we now know that the universe is anything but static. In fact, the universe is not only expanding, but the expansion is accelerating. This suggests that all of space is under a force to expand, which makes me think what we need is to reconsider general relativity in a more dynamic way, like acceleration and vectors rather than curvature and tensor. This isn't even crazy, because Einstein himself already suggested that curvature is equivalent to acceleration with the postulate of equivalence, which is already in general relativity. Thus, we could swap them without needing to make drastic changes. And this would eliminate the need for the postulate of equivalence in the first place, because then a gravitational field would actually be an accelerated frame of reference. You see, when Albert made the postulate of equivalence, he was speaking about the equivalence between a spaceship at rest on Earth in comparison to a spaceship accelerating at 9.8 meters per second squared in deep space. He suggested there was nothing a person could do inside of the spaceship to determine through experiment which situation they were in. However, we now have the ability to solve this conundrum by using quantum clocks. These clocks have the ability to measure a difference in the rate of time within a mere few feet in a gravitational field. So if we had two of these clocks inside the spaceship and we set one on the floor and the other on the ceiling, then we would expect to see a difference in the rate of time between these two clocks when we are within a gravitational field. Whereas, when accelerating through space at 9.8 meters per second squared, we would not, because then the two clocks would be experiencing identical motion through space and thus identical motion through time. Unlike in a gravitational field, where the fall off of the effect of gravity means that these two clocks will have different rates of time due to their different distances from the gravitational source. Now, even though I am showing that we can determine a difference through experiment, I'm not suggesting that Albert Einstein was wrong. Instead, I suggest he didn't go far enough. If Albert had followed through on this thought experiment to the other half of the journey with the spaceship that was accelerating at 9.8 meters per second squared for the first half of its journey, it would then have to flip 180 degrees in order to decelerate for the second half of its journey, in order to slow down and avoid crashing into its destination. This would mean that the orientation of the spaceship relative to its frame of reference is now reversed, where the momentum of the spaceship's crew is now towards their feet because the reference for motion, which is space, is now moving towards their head. This is how I imagine we are orientated relative to our spatial frame of reference, which would mean on Earth, our momentum is towards our feet because space is being accelerated towards our head. This may seem counterintuitive to receive momentum from the acceleration of space until you understand the reason for the shape of the parabola in the water of Newton's bucket. As Isaac Newton's bucket experiment suggests, the shape of the water in his bucket is due to its relative motion through space. This experiment shows that space is the ultimate frame of reference for motion, which means that the acceleration of our reference frame would cause us to have momentum in the opposite direction, thus curving our path through time and space, similar to the way the wind would curve the path of an arrow through the air. Only space would act in the opposite direction to that of wind. That might seem counterintuitive, but it is exactly how Isaac Newton's laws of motion require it to work, since according to Newton's laws of motion, Your momentum is always in the direct opposite direction to that of your local frame of reference, which is space. This means that if space is being accelerated outwards from the Earth, then we would receive momentum inwards towards the Earth, and this also explains why we receive time dilation within a gravitational field. Since we are in motion relative to space, then we receive time dilation for the exact same reason we receive time dilation within special relativity, which is our relative motion to space. To understand how space is being accelerated outwards from the Earth, we must first understand that matter is mostly space. For example, if you were to take something the size of a large skyscraper, and you were to take out all of the space, leaving only its matter behind, it would be about the size of a grain of rice. The rest of the skyscraper is space and energy. Thus, the energy that is expanding all of space would also be expanding the space that is within matter as well. However, the subatomic particles of matter would distort this expansion because they are being held together by the forces described within quantum mechanics. These subatomic particles would act in a similar way to that of a nozzle on the end of a garden hose. Space, just like in the case of the water, would come out of the hose, receiving an acceleration caused by its restriction of flow. That means that the density of subatomic particles and the amount of energy holding them together would dictate the strength of the force of gravity, as we observe it does. Therefore, I assert that dark energy is not only the cosmological constant, but it is also the source of the gravitational constant, which means that the Earth's large amount of matter is both accelerating space and decelerating us, the combination of which we feel as a force we call gravity. The way relative acceleration works is quite unique, since we only feel it when we resist it. The reason for this is because the entirety of us receives this acceleration at almost the same time, which is unlike kinetic acceleration, like the acceleration we feel in a rocket. When the propellant pushes on the engines, and the engines push on the ship, and the ship pushes on our seats, and the seats push on our skeletal bodies, and our skeletal bodies push on our internal organs, thus we feel kinetic acceleration as a sequential acceleration, whereas when we are accelerating relativistically by our frame of reference, we do not. This is because the synchronous nature of relativistic acceleration. To feel the acceleration, it needs to be resisted. Kinetic acceleration is resisted by our frame of reference, whereas if the frame of reference itself is being accelerated, then we feel nothing. You can imagine relativistic acceleration as if every subatomic particle has its own tiny little engine. Then they would all accelerate together without collision, and thus no force is felt. Also, by putting general relativity in motion, we have solved some of the mathematical problems of combining it with quantum mechanics. This has been an overview of how space and matter come together and create the laws of relativity from my book, Temporal Quantum Relativity. If you want to find out how this sheds light on dark matter, black holes, and the birth of the universe, you might want to check it out. You can find the links in the description. But don't worry, I wrote Temporal Quantum Relativity for everybody. So I left out any equations and instead put in many drawings to help get these difficult ideas across. And of course, please subscribe to get my next video for this series, where we will tackle those tricky time paradoxes of special relativity.